Now that we've examined the Jovian planets and their large moons, we're going to turn our attention to smaller bodies in the outer solar system, comets. Now, comets have been seen for many centuries by many cultures. Often these surprise visitors were viewed with alarm, even panic. And yet today we know that they pose very little danger to us. The first real breakthrough in understanding comets came in the early 1700s when the English astronomer Edmund Halley began to study the orbits of comets. Now, Halley noticed that 3 comets in particular that had been recorded had the same orbit. He thought that perhaps this didn't make sense. Why would 3 comets have the same orbit? Instead, he realized that indeed it was the same comets in an extended orbit, appearing approximately every 75 years. So this began to bring comets into the realm of our study, knowing that many of them would return. Halley was even able to predict its return in 1758. So what are comets? Oftentimes we see a picture of them with this bright tail. Well, let's go back to our discussion of the beginning of the solar system and its formation. We said that in the outer solar system it was cold enough for gas and ices to survive, and that these small particles would slowly, gradually stick together and form little larger particles and larger. And eventually these would become, as we called them, planetesimals. Well, these planetesimals in the outer solar system, there was a vast number of them, obviously, to create the Jovian planets and their satellites. But remember that there now is vast distances in the outer solar system. And the great distance between many of these particles meant that some of them would not collide. They would not grow much larger. And so we would end up with some bodies that simply did not get very large. Perhaps a few hundreds of feet, thousands of feet, perhaps a few miles across, and they would be composed primarily of ice. Well, this is what we see today as comets. Relatively small chunks of ice orbiting in the outer solar system. So we could think of them as essentially leftover icy planetesimals that never formed a larger body. And so these comets pretty much stay in the outer solar system for millions and millions of years, just quietly orbiting the sun at great distances, but they're so tiny we really can't see them very well from Earth. We do see them when they obviously begin to approach the inner solar system. Once in a great while, one may feel a very slight tug or pull or nudge gravitationally that would change its orbit enough that it would begin to fall inwardly towards the sun. Here's where we can get a close-up view of these comets. So as this chunk of ice is falling towards the sun, of course it's going to slowly warm up. Now the ice won't melt into a liquid, but it will begin to do what we call sublimate, that is, change from a solid to a gas. So as the comet begins to approach the sun, it sublimates, begins to give off this gaseous cloud around it, and we call this cloud the coma. The coma. As a comet gets closer to the sun, if it gets close enough, that coma can grow dense enough that the pressure of sunlight can literally push away some of that cloud and form a tail behind the comet. Now some particles of ice and a little bit of dust mixed in are going to reflect the light, and you and I would then see that tail. But interesting, some parts of the gas themselves could be broken apart by the sun's ultraviolet light and begin to give off a very weak, faint light of their own. This we would call a gas tail or a plasma tail. So let's take a little closer look then at, again, the anatomy of a comet. And you can see here a typical comet showing the dust tail, the plasma tail. And if we were to zoom in and somehow look into that nucleus, into that coma, we would see the small solid nucleus. You see in our next diagram here a picture showing, again, how that orbit would work. The comet, again, at great distances, orbiting very slowly. As it approaches the sun, would warm up, begin to sublimate, and again, tails would be pushed backwards away from the sun due to the pressure of the sunlight. So this gives us a good first idea of the nature of comets. Although for many years we studied them, we could get a pretty good idea, but we never could see them up close because that solid nucleus was pretty much hidden within the coma. Well, different theories were put forward to suggest that perhaps that solid nucleus was, again, a chunk of ice, kind of a dirty snowball, so to speak. But recently, in recent decades, we've actually gotten close-up looks at the nucleus of a comet. The first opportunity was back in 1986. The European Space Agency sent a spacecraft to visit the famous Comet Halley, which had been seen many, many times over the centuries. And you can see here the historic first pictures of the actual nucleus of Comet Halley taken by that spacecraft. You notice that the ice is not sublimating or being spread out evenly, but rather it's very patchy, so to speak. Really only the face of the nucleus that's towards the sun is giving off much ice and gas. Of course, that nucleus would slowly be tumbling in space, and different areas would give off a little more or a little bit less, and so you get a somewhat uneven distribution. Well, some years later, NASA sent the Stardust spacecraft to take a picture of a comet nucleus, as you see here. And the Stardust spacecraft was able to reach out with a small collector and literally capture some of the small particles of dust and other materials, sealed that up. Its orbit brought it back towards Earth, and that container then was deposited back on Earth, and scientists got their first opportunity to actually get their hands on a little bit of comet dust to study their composition. Shortly thereafter, the Deep Impact spacecraft visited Comet Tempel-1, and here a little different experiment was executed. As the comet nucleus was flying through space, a projectile was pushed out in front of it, and as the comet crashed into it, there was a tremendous impact, and you see here the results. The main spacecraft took this image in the lower left, showing a fairly dark nucleus, and yet when the impactor struck, much fresh, brighter ice was exposed. Even from Earth, the Hubble Space Telescope was able to see a tremendous brightening in the comet because of this. The purpose of the experiment was, of course, to obtain these images, but it did give us also a much better indication of the density of the comet nucleus. We hadn't been quite sure if it would be very hard rock type of ice that you and I are used to, or more of a lower density, fluffier type of ice, more like snow. Well, interestingly, it turned out to be the latter. The composition indicated somewhat of a lower density, fluffier type of ice that the comet nucleus was made of. Over the centuries, it seems that as the comet would come in and some of the ice would be sublimated away, some of the darker dust material would remain, and as a result, again, the nucleus looks somewhat dark here. Well, our most recent mission has been a very exciting one. The European Space Agency sent the Rosetta spacecraft, and notice the comet that it visited here, the nucleus, very bizarre, strange-looking object, almost appearing that perhaps two objects were stuck together. And so this possibility is being considered. It's also possible that one particular object just lost more material around its center. We're not quite sure just yet. Amazingly, as the Rosetta spacecraft was orbiting the comet nucleus, or very slowly and mapping it, taking many pictures, it carried with it a small lander called the Philae lander. This lander was able to successfully touch down and provide us measurements of the surface density, again showing a relatively low density. After about a year or so, as the comet swung around the sun and Rosetta was able to monitor its activity over an extended period, the comet began to move far enough from the sun that the spacecraft would no longer have enough light for its solar panels to generate electricity, and so the mission would need to come to an end. Well, Rosetta was successfully itself set down onto the comet's surface, providing us some very exciting close-up pictures during its final descent. But let's go back and explore just a bit further the origin of the comets. We said that they were formed in the outer solar system as large planetesimals. Well, interestingly, over the years, several different astronomers carefully studied a large number of comets' orbits. And interestingly, two main families or groups, so to speak, began to stand out. One astronomer, Kuiper, noticed that there was a group of comets that tended to have a relatively short period to their orbit, perhaps less than 200 years. And he noticed that most of their orbits were pretty much in the plane of the solar system, the plane in which all of the planets orbit. Another astronomer, Oort, noticed something different. He found that there was a large number of comets in very different orbits, very, very large orbits requiring hundreds, if not many thousands of years for them to circle the sun. And these orbits were at various inclinations, really pretty much at all inclinations to the plane of the solar system. So these two groups became known as the Kuiper Belt and the Oort cloud. And so today we examine a comet as it approaches and get a good idea of its orbit, and we can pinpoint and say, well, this comet appears to have come from this flattened region, perhaps the Kuiper Belt. Its orbit may be less than a few hundred years, but we may on the other hand notice that a comet approaching the sun is coming at a very different angle to the plane of the solar system, that ecliptic, and it may be a much larger orbit, many thousands of years. Well, we begin to realize that's from the Oort cloud. How did these two groups appear? What's the origin of these two groups? Well, you might recall we mentioned briefly that when the solar system formed, we found that the forces involved caused the planets, again, to take up orbits very much in the same plane. And that's why they orbit there. Well, likewise, we think most of the early comets, or icy planetesimals, would have also taken up a relatively flattened type of distribution around the sun at great distances, and we still see many of those left today as Kuiper Belt comets. What about the Oort cloud? Well, here we've learned in recent years that many of these objects over the course of the solar system would approach one of the large Jovian planets, and the gravity of these planets would literally change the orbit of these small icy objects, flinging them out to great distances and at every random inclination, essentially giving them a new orbit, much farther out, and again, roughly a spherical distribution. So it's very interesting to be able to see a change here over the course of the solar system, that again, many of these small objects were sent out to these much larger orbits. There's even thought that this is probably a very likely occurrence, possibly around other stars as well. They may as well have these outer clouds of small icy objects that are orbiting them. So we've gotten a nice introduction to comets. We saw them again as small icy planetesimals that never fully formed larger objects. Many, many, many millions of them orbiting in the outer solar system. These chunks of ice can have varying densities. Some are going to be much more dense, others are going to be much less dense. Normally they orbit far from the sun and we don't see them until they happen to come to the inner solar system. When they begin to experience the sun's heat, the ice sublimates. We see that coma grow, and often when the coma gets large enough, the pressure of sunlight will push back a tail that you and I can see, whether it's reflecting the dust or whether some of the gas molecules themselves are broken apart and in doing so give off a very faint light. Where do comets come from? Well, we saw that they pretty much formed in the plane of the solar system, out beyond Neptune, in the Kuiper Belt that we see today. And yet a large number of these objects had their orbits changed by the Jovian planets. Over long periods, as they encountered these planets, the gravity of the Jovian worlds would send them out to a much larger orbit at all types of random and varying orientations. So we've been able to learn quite a bit about the comets in recent years. They play an important part in our understanding of the solar system. In our next lecture, we're going to continue to examine the outer solar system, and we'll finish up by looking at objects in the Kuiper Belt that are significantly larger than comets, but smaller than planets. And yes, we'll finish up as well with the discussion of Pluto.